Welcome all of you. Today we demonstrate the offline condition monitoring of transformer using frequency response analysis. As we know, the transformer can be considered or analyzed as a distributed network of resistances, inductances and capacitance. Hence, its frequency response can be analyzed for different condition of transformer. These conditions are like normal condition, fault condition, etc. This test is performed on the special designed 10 kVA transformer for the interturn faults and coil displacement fault. This transformer can be connected for turn ratio of 400 to 200 or 400 to 100. This transformer have also tertiary winding for the auxiliary purpose with rating of 30 volt. See the HV side current rating and LV side current rating. Transformer can be connected in delta star, star delta, delta delta, star star connection. You can see our 10 kVA special design transformer. This is the HV side of this transformer. These tappings are brought out for the different purpose like the interturn short fault. Similarly, this is the LV side of this transformer. The secondary also tapped for the different purpose. This is the tertiary winding of this transformer. This is for the auxiliary purpose. Now we'll see the plate of this transformer, that is the rating which make of this transformer. We already discussed this. Here you can see the HV winding and LV windings tappings. These tappings are brought out deliberately for the different purposes. Same thing is given in the that plate on the transformer for the HV and LV side. Now we'll see the connection of the transformer, in which fashion this transformer is connected. On the nameplate you can see the connection for the different vector group, that is YD1, DY1, YD11, DY11 and YY0, that is star star. Now we'll take the brief view of the internal design of the transformer. Here you can see the core of the transformer, that this is outer part of the transformer. These are the windings, that is tappings brought out from the coils. This we'll see now how the coil is placed. This coil is arranged, that is the segregated in four part intentionally to do the displacement fault. You can see that the 4 coils. Now we'll see the surge coil. What is the surge coil, how it placed in the transformer. Construction features of the surge coil is similar to your HV or LV winding, but it has very less that is turns, that is 1 or 2 turns. Why it is designed? It is designed for the purpose of measuring the voltage to analyze the different condition of the transformer. Here you can see the surge coil wound on the HV winding. Similar design is done for the LV winding. Now these winding are, for the simplicity, these winding are brought out. We can see from this side. These are all the that is winding, surge coil windings. These are brought out for the measurement of voltage. Here now you can see this red color is for the A, that is U phase, this for the V phase and this for the W phase. There are 6 coils are wound on the HV side, HV winding, and 4 on the LV winding. Now I will see the types of fault for this transformer. There are 2 types of faulty transformer, that is the interturn short circuit fault and coil displacement. Here you can see the that is coil displacement fault by displacing the this coil, and interturn short fault can be done by shorting this tapping, different tappings brought outside. Now we'll see how this frequency response is analyzed. This is analyzed on the impedance analyzer. This is a device. We'll see this device how it works. This is a key side impedance analyzer having the range of 20 Hz to 10 MHz. You can see the screen of this impedance analyzer. Now we'll see the instrument setup. This is in the mode of the trace CS and CP. Now for the sweep type, that is your this x-axis, that is the lock type, that is frequency. Then you can select the start stop frequency by entering or by selecting these values. Then you can select the number of points more is the point, you will get the more frequencies values. Now with the mean times for the mistype for the how the accurate your value. If you select 5 value, then your system, it will sluggish your system, so we'll select it as a 1 as a fast. Now I will select the y-axis, that is your value z and phi, that should be the linear. Now we'll enter into the marker, because we have to mark the value of different frequencies. So that we will the mark for the marker 1, I selected here the 20 hertz. Similarly, I will take the marker 2 and will select the values, that is the 200 hertz. Then similarly for a marker 3, selected as a 2 kilohertz, as we have to analyze the value of 2 kilohertz. Then for the marker 4, the value is selected as a that is 20 kilohertz. Similarly, uh, for by pressing this next option, that is more marker, it is I will select the marker 5. It is by wrongly, now the marker, it is actually selected as a marker 4. Now we have to select the marker 6, that is the 2 megahertz. In this way we select the markers. Now we can see the values of this marker for the first, that is this is your z value and this is your phase value. Now we have to measure which trace. Now we have to measure the z and their phase. So your upper part is your impedance and the lower part is your phase. To check the condition of the transformer, windings is connected to the input terminal of this impedance analyzer. Now we perform the frequency response analysis test on the transformer. First we will observe the frequency response for normal condition. Then we will observe the frequency response analysis for that is fault conditions, such as short circuit for intermittent short circuit fault and core displacement fault. Now these are the results for the healthy condition, normal condition, when the W phase are connected to input of this impedance analyzer. You can take the screenshot for this of these results. Next we'll do the 2% shorts fault, that is intermittent shortfall of the 2% turns. This fault is done with the low resistance. Now we'll see the how it affect the our impedance. You can see now this graph of this impedance and phase changes. See this. Now these are the marker points value for different frequency. You can take the screenshot for these. Now these are the value of the phase angle of that particular frequencies. Similar way we will do the 5% fault by shorting the 5% of the turns. Here we are doing the 5% fault. Now we'll see the effect. You can see the effect. And now we'll see the value of marker 2. First the value is 733. Now it changed to 571. Similarly, you can see at the third and others marker, it will run fast at the high frequency. Now same way will short the 10% of the, that is your turns. In this case you can see the changes at the z and at the their phase of the particular frequencies. In this way we perform the intermittent short circuit fault. Now we'll do the coil displacement fault. For that, first you have to make the transformer in healthy condition, so we'll remove that connections. Now we'll see the value of the z and phase at the healthy condition. Now these are the values of Z and phase at healthy condition. Now we do the one coil displacement fault by displacing this coil. See this. Now we'll see the effect of this coil displacement. Now we can check the effect. See this, it will changes this marker point value of this Z and phase. This is the results for your one coil displacement fault. Now similar way the will perform the two coil displacement fault by displacing the second coil. You can see this how to displace this coil. Now this how this affect the your impedance and phase. You can see these are the results for the your that is two coil impedance or two coil displacement fault. Now next is you have to take this means you have to save this result. How to save? So first you have to go to system, then demo screen image, then you have to give the name, or we will give the name demo and save this. Now we'll see that position of that results. So this is demo result. Now see, you can see you can store like this. Now we'll see the comparisons amongst the different conditions. So you can see that the effect of the 5% intermittent fall and 10% intermittent fall on the middle ranges frequency is more. The value of Z is decreasing in this case, and in the case of the coil displacements fault, the value of Z is increasing at middle frequency range, and for other frequency ranges the value are decreasing with very less magnitude. From this you can detect the interturn short circuit fault and coil displacement fault under miss or in offline conditions. Hence this is our complete demonstration of this FRA experiment.